Hello everyone. In the previous video, we have looked at an alternative formulation of the buckling theory, and at the end of that video, we had said that how that alternative formulation and the insights gained thereof would help us to make some headway into a more exact theory. So that more exact theory is what is going to lead us to the equation of the Elastica. So this rather exotic name is there because of some historical reasons. It has been investigated for quite a long time by mathematicians. So, so we'll respect that history and name our topic of discussion as the Elastica. Okay. So what we are going to do is to go back to a certain point in that alternative formulation, pick an equation from there and proceed from there. Okay. So let's go back. So this is the first slide within our previous video, and what we are going to pick out is this particular equation at the end of this slide. Okay, so let me just copy it out. There are a number of disadvantages to uh, using this writing app, but one big advantage surely is this copy paste business that I'm allowed to do here. Okay, that certainly saves a lot of time. Okay, uh, the first thing that we're going to do is we are not going to consider this kind of a lateral force. Okay, so that is zero. Uh, Let me write that down in a better fashion. All right. With that out of the way, what I'll do is I'll just repeat this thing, the left hand side remaining as it is. But uh, the right hand side, that I will rewrite as half 0 to L T delta dw dx whole square. Okay, I believe no one should have any problem with me writing this as this. Okay, all right. So what I'll do is I'll take this. The plan is like this. So I'll take up this left hand side and this right hand side separately, and then I'm going to utilize whatever insights I have obtained previously, as well as uh, my uh, my knowledge about the geometry to uh, to go from this version of the equation to a more exact version. Okay, so the first step towards that goal is to identify that in the left hand side what I have, this d square w dx square, that term is basically an approximation of the curvature of the beam. Okay, so uh, we have mentioned this earlier in a previous video that and this basically follows from our knowledge of first year engineering mathematics, where we talked about uh, curvature of a general curve. Uh, so d squared w dx square is an approximation of the curvature of the beam, which is uh, if you refer to your first year engineering mathematics books, you will note that the general formula for the curvature is given by this. The whole thing is within a 3 by 2 power. All right. So what we basically say is that if dw dx is not too large compared to 1, then, or is rather small compared to 1, then this entire term, it basically reduces to d squared w dx squared approximately. Okay. So now we want to go from in the reverse direction. That so we identify that this indeed is an approximation of this, and that is the curvature of the beam. So how could we rewrite this term using that knowledge that it is indeed the curvature? Okay, so that is the question we pose to ourselves. Okay, so uh, so what we do is, as we have done in the previous video, we are going to go from this xz coordinate system to the s theta coordinate system. Okay, so I'm not going to draw that again. So in the s theta system, in the s theta coordinate system, the curvature uh, is given by d theta ds. Okay, so uh, you identify, first of all, you observe that how I mean, just by choosing a different coordinate system, this s theta coordinate system, how the expression of the curvature, it is just even visually much simplified compared to this rather complicated looking expression. Okay, now that is about the left hand side. Now from the right hand side, what we have on the right hand side, we have this half dw dx squared. And remember, in the previous video, when we were talking about the alternative formulation, we had already noted and justified that half dw dx squared is equal to minus dus dx. Okay, so this was about the LHS. Okay, so from the RHS, what we have is uh, this half dw dx squared, that is equal to dus dx, but with a negative sign. Now, uh, how can we use this thing? Okay, so uh, you note that if I consider the integration of this, okay, so you see the only difference, if I just consider the integration of this, is the first variation. So we'll deal with that later. Okay, so uh, so if you consider the integration of this, perhaps there is some hope that it could be written in terms of the s and theta, because after the integration is done, perhaps we can write this in terms of the L and the delta L in those terms. So let us proceed in a systematic fashion and see what can be done about this. Okay, so what I'll say first of all is that since we have this thing to be equal, let me actually write the equal to sign here. Okay, since this is equal to this, uh, if I consider this integration, from 0 to L, you note that immediately this thing is uh, nothing but delta L. Okay, this is nothing but delta L. Now, if you're a little bit careful and very observant, you will see that uh, okay, I have written it like this, But in the previous video, what we had uh, really written or found out was something a little bit different. Okay, so let me just show you what's the difference. Okay, you have this thing, uh, this dus dx, all that is fine. We have an integration also, uh, but there is the limit. Okay, this limit is L minus delta L. That is not quite the same here. Okay, of course there's a negative sign also involved, but that's not the issue here. What I wanted to show was that there is a L minus delta L here. So this delta L is, so I'm just showing you again. So previously what we had shown was that this integration 0 to L minus delta L dus dx, uh, that is equal to minus of delta L, okay, or the other way around. And what we are saying now is that this thing with the 0 to L, that is equal to delta L. So there is a little bit of a mismatch. Okay, so I have cheated a little bit. Okay, a bit of mismatch with what we had shown earlier. However, we'll see that it doesn't really cause much of a problem, only because especially if this delta L is not too large. Okay, now the good news, however, is that this delta L, we have already obtained, we have already written earlier in terms of the S and theta. Okay, so you see what we are trying to get at. In the left hand side, by identifying that this del d square w dx square is an approximation of the curvature of the beam, we have written that curvature in terms of the S and theta coordinate system, in terms of this d theta ds. On the right hand side, whatever there is, whatever geometrical arguments we are talking about, ultimately we should be able to write this thing in some form involving the S and theta. So how can we do that? Okay, so we have already done the work regarding that. So let me just go back and show you. In the previous video, we have already obtained this expression. This delta L is equal to this thing. Okay, so uh, uh, there was a little bit of a mistake here, because when we go from the 0 to L minus delta L dx and we change the limit to ds, it should actually be L, because you see this S is going like this. Okay, so I'll make that correction here. When we are writing in terms of the x here, that is fine, but this should be in terms of 0 to L here. Okay, all right, so what we'll do is we'll write this delta L as ds minus 0 to L ds cos theta. Okay, now the left hand side is in terms of this d theta ds, okay, and the right hand side is in terms of this. But please note that this, we have to take care of this first variation, and on the left hand side also we have to take care of this first variation which is present here. So let us put everything together, okay, in the next slide. So 0 to L ei, let's check what we have. We have d square w dx square, that is the curvature, and that can be written as d theta ds. So let's write that, d theta ds. Next we have this d square delta w dx square, which is basically just the first variation of d square w dx square. So this can be written again as d delta theta ds. We have basically just taken the delta of d theta ds and taken this first variation inside the differentiation. Okay. So this is all set, the left hand side. The right hand side, let's check. We have this p can go out of this integration, no problem there. So we have this half uh, delta dw dx square. Okay, and we have just seen that this half dw dx square is this entire thing. So what we really have to do is take the delta of this entire thing, keeping in mind that the p should be also outside. Okay, so let's do that. So p goes outside. We take the delta of this whole thing, whatever we have obtained here, that is 0 to L ds minus 0 to L ds cos theta. So this left hand side, we are again going to carry out an integration by parts. That leaves us with this delta theta in this boundary terms minus integration 0 to L dds of ei d theta ds. So that's the differentiation on the first bit, and then we have this delta theta. So this is my entire left hand side after the integration by parts. And on the right hand side, if I carry out this first variation, you see this term is just the L. Okay, the 0 to L ds, that is just the capital L. So that's a given to us. There is no question of variability in it. So the first variation of that is certainly 0. So that leaves us with uh, this uh, minus of delta 0 to L ds cos theta. And what we are going to do is we are going to take this delta inside. This delta is going to operate on this cos theta. Okay, so since in terms of operation, uh, the delta or the ordinary derivative or the ordinary differentiation differential, it acts in the same way. So what we are going to have is ds minus sine theta delta theta. All right, so overall what we are obtaining is just this. Let me just write it out here itself. Okay, so basically what is going to happen is this this minus and this minus, it becomes a plus. Okay, so I just have this. All right, so this is an integration on the left hand side with respect to s, having this delta theta. On the right hand side, I have another integration with respect to s, and it contains in the integrand this delta theta. So for my governing differential equation, what I will have is this term or this integration considered together with this thing, and then we take the coefficient of this delta theta, which is ei d square theta ds square. Please note that I have considered this e and I to be invariant or constant with respect to s. So I'm taking this out of the differentiation. And then I have this plus, sorry, I forgot the p here, bad mistake. So plus p sine theta, that is equal to 0, because there are no other terms involving the integration with respect to s. And for the boundary conditions, you please note that we have only just this one term involving the boundary. So at x equal to 0 and x equal to L, what we have is either EI d theta ds is equal to 0 or theta is specified. Okay, so this set of equations that we have obtained, this governing equation together with these boundary conditions, these are said to be the equations of the Elastica. And you please note that how in the entire procedure, okay, so once we have obtained this kind of a statement using the calculus of variations, the obtaining the governing differential equations and the boundary conditions could be done in a nice mathematical fashion without even worrying about the actual physical setup. Okay, we don't even have a real physical setup in our hand unless we have been given an actual problem, which of course we'll take in the next video. But uh, we have done this in a nice analytical fashion. Okay, so it would be nice to have a little interpretation about this. So what is going on here is that this theta is specified means that the either the slope is specified, okay, or if the slope is not specified, then what we'll have is this ei d theta ds equal to 0. Okay, so you think about what this thing is really telling us. Okay, so this is the, mind you that this d theta ds itself is just the curvature. Okay, so uh, uh, there is your hint. Okay, you think about what this d theta ds, the curvature, would be in terms of r, the radius of curvature, and then see what that ei divided by the radius of curvature denotes. Okay, so I've almost given you the answer, but you think about it anyway. All right, so with that we have our a more exact version of the buckling formulation, and using this we can solve some problems, and that is exactly what we'll do in the next class. We'll solve one problem. Okay, and that will teach us a lot of some big lessons. Okay, all right, on that note I'll end this video. Thank you very much.